Okay, here we go. 8.2. This is the last section. This is the last section in the second to last chapter of the year. Polar area. Again, one of my favorite things that we do all year. So we know how to generate polar curves now by rotating and then going out a certain distance. But if I wanted to figure out, let's say, what the area is between two angles, call it alpha and beta, and my curve is the red curve right there. So remember, the radius can increase or decrease as we rotate, which, by the way, that's what dr d theta gives us. Okay? We've been taking the derivative of y with respect to x, but dr d theta tells you how fast the radius changes. It's the change in the radius per rotation, which would be in radians. Okay? So if dr d theta is positive, then our radius is getting bigger and we're moving away from the pole. If dr d theta is negative, then the radius is getting smaller and we're moving towards the pole. So in that variation, you get a curve that looks like this. And it's not a perfect arc, but we can use an arc length formula to help us derive polar area. So remember that if it was perfectly circular, like a pie, I don't know if pizza pies are perfectly circular, we had a formula, S equals, well, we're not doing arc length, sorry, the area of this sector here. If we want to find the area of the slice of the pizza, the area of the sector was 1/2 r squared theta, where theta is the central angle in radians. Well, we can use that same idea, and remember, if we can write it as something times d theta, we have it. If this curve is not really a circular curve, we can make the angles smaller and smaller and smaller. And as the angles, wedges get smaller and smaller and smaller, we can start adding up these little bitty sectors that approximate the curve, because these sectors are still circular. So you can, again, see the idea of the limit. As we put more and more sectors in there, we kind of converge towards the actual area. So I'll just jump right to the formula here. The formula for the area of a polar region is 1/2 r squared d theta. And again, it comes from the area formula of the sector. It's basically doing this. We're taking the individual sectors, which are 1/2 r squared, and then delta theta, which are finite and measurable, and we're adding up all those areas from alpha to beta, but then we're taking the limit as n, the number of them, goes to infinity, and of course we know how that works. Delta theta becomes d theta, and we get our formula for the integral. So you have to memorize it. Okay, what is the formula for the area of a polar sector? Yeah, very good. 1/2 r squared theta. That's how you have to say. It's 1/2 r squared theta. But the 1/2 being a constant multiple can come out front. And of course, the theta is really d theta because we're making it infinitely small. And then the radius squared is your integrand, and we're going from alpha to beta. So 1/2 r squared theta. It comes directly from the formula for the arc length, or the area of a sector, of a circle. Sorry. All right, so let's try it out. Example 1. Find the area bounded by the graph of 2 + 2 sine of theta. So it's not important or essential, I should say, to know what this graph looks like, but it is kind of fun and it helps orient yourself. Do y'all remember what this graph would look like? It's a cardioid. Good. Now, to get a real quick sketch, just plug in your quadrantal angles and see what you get. So when theta equals 0, you get 2. So that's where it starts. When we're pointing due north at pi halves, sine of pi halves is 1. So that's where we're going to get 4. When we're pointing due west at pi, sine of pi is 0. We get 2 units again, so we're at -2. And then when we're facing due south, that's 3 pi halves. Sine is -1, and that's where we get our polar 0. So this, and then it finishes off. So this graph looks like this. Boom, boom, something like that. All right, so what we want to do is we want to find the area of that cardioid. All right, and we're not going to do it the same way we did with rectangular area. We are going to find the area by sweeping arcs. So here we go. This one should be pretty easy, but I'm going to start at 0, at theta equals 0. And if I just start taking small little sectors, that's what this is. I'm finding all these areas, We're rotating the pi halves. Now we're rotating all the way to pi. And then I'm rotating all the way to 3 pi halves. And then from 3 pi halves, I rotate all the way around to 2 pi. And if we add all those little sectors up that I just drew, we should have the total area. So here we go. Remember, we abbreviate area, AREA. It's going to be 1/2 r squared theta. So the 1/2 is up front. It's going to be the sum from theta equals 0 to theta equals what? 2 pi, and then of r squared d theta. Now, r is the equation that we're given. It's 2 plus 2 sine of theta. Okay. Now, from here, once we have the setup, the question is, how are we going to be expected to evaluate it? If it's a calculator question, you probably have just graphed that on the calculator instead of doing it by hand. Once you show this integral setup, you could, of course, go to the calculator and evaluate it. But you might be asked to evaluate this also by hand without a calculator. So we're going to do that first, and then we'll verify on the calculator. All right, so here we go. This is going to be a little bit of work. 1/2 out front. What am I going to have to do with my integrand in order to make it workable? I'm going to have to expand it, right? Because if I let this be the inside function, its derivative is 2 cosine of theta, and there's no cosine of theta on the outside, so it's not just a power rule. So we'll expand it. Square multiply double square. Square multiply double square. So we get 4. When you multiply, you get 4 sine. Double it, you get 8 sine. And then you square the last, you get 4 sine squared. So plus 4 sine squared. D theta. Now you take inventory. We have 3 terms. The first term and the second term we can easily antidifferentiate. But how do we antidifferentiate plain old sine squared? Polar area is where the power reducing identities become very, very relevant. So let's review those very quickly here. Cosine squared of theta is equal to 1/2 times 1 plus cosine of 2 theta. And sine squared of theta is equal to 1/2 1 minus cosine of 2 theta. So they're very, very similar. Cosine, they're both in terms of cosine. So cosine squared gets the positive sign because it's in terms of cosine, and he's selfish, so he wants the plus sign. It's more coveted. And then the sine squared gets the minus sign. So remember, the cost of reducing the power by a factor of 2 is you double the angle. Okay, you half the power, you double the angle. So let's go ahead and rewrite sine squared as 1/2 1 minus cosine. So I'm going to have a 1/2 integral from 0 to 2 pi. And we have 4 plus 8 sine of theta. And when I replace sine squared with 1/2 times the blob, I have 4 times a half, which I'll simplify that, I guess, on the next line. And then sine squared becomes 1 minus cosine of 2 theta. Close, close, d theta. All right, one last thing that I'm going to do is I'm going to distribute. So I'm still writing this entire integral again, and I'm going to take the integral of everything at one time, not in parts. So 4 times a half right here, that's 2. If I then distribute the 2, I get plus 2 minus 2 cosine of 2 theta. Now, man, there's one last thing we can do, right? We can add that together and get 6, and then if you want, you can even factor out a 2. You want to do that? All right, let's do that. If I factor out the 2, that's going to be nice because the 2 and the 1/2 up front are going to divide out. So I'll show that. There's the 1/2. We're going to factor out the 2. So it's 0 to 2 pi. Now, what am I going to be left with in my number? If 4 plus 2 is 6, and I factored out the 2, I'm left with 3. Good. And then plus 4 sine of theta, and then minus cosine of 2 theta. So this is a lot of manipulation just so that everything runs smoothly, which is why if you had to do this by hand, you probably wouldn't be asked to do it more than once. Okay? All right, I think now we're ready to go. So our coefficient out front is now just a 1. That's cool. So we don't have to worry about parentheses and distributing. So the antiderivative of 3 with respect to theta is 3 theta. The 4 goes along for the ride. The antiderivative of sine is negative cosine, right? So if you're not sure, guess, check, and revise. What would be the derivative of negative 4 cosine? Positive 4 sine. So we got it. So there's that negative right there. And then over here, I got minus. we have an inside function of 2 theta. That's the blob. What's the derivative of 2 theta? 2. So I'm off by a 2, so I'll have a correction of a half. And now what's the antiderivative of cosine of blob? Just sine of the same blob. And now I'll evaluate all that from 0 to 2 pi. So plugging in the top, we get 3 times 2 pi, which is 6 pi, minus 4 cosine of 2 pi, minus 1/2 sine of 2 pi times 2 is 4 pi. That's plugging in the top. Minus, same thing, plugging in the bottom, we get 0 minus 4 cosine of 0, minus 1/2 sine of 0. What's sine of 0? 0. So we wipe all that out. Well, let's keep going. We get 6 pi, and then a cosine of 2 pi is the same as cosine of 0, which is 1. So we have minus 4. What's sine of 4 pi? 0. So 6 pi minus 4 is all we get from the first plug-in. And then we're going to have minus 0, minus, okay, what is cosine of 0? 1, right? So all that we have from the second plug-in is a negative times negative, which is positive 4 times 1, which is positive 4. And we end up with the answer, 6 pi. Pretty remarkable then. So this palm leaf or whatever, or a lily pad looking thing, cardioid filled in, is an area of 6 pi square units. Okay? So the power reducing identities show up very often when you have to do these by hand. Now, before we go to the calculator, let's think about another way we could have done this. This one works nicely when you trace out your radial lines. That's what I was doing here. When you draw the line from the pole to the curve, those are radial lines. You can go all the way from 0 to 2 pi. Can you use symmetry here? Yeah, since this one has y-axis symmetry, you could also do this. You could double it, so it'd be 2 times and then 1/2 the integral from. Now to double it, remember when we start at 0, we're facing due east. So I'm actually going to have to back it up to here. So I would go from negative pi halves, which is coterminal with 3 pi halves, all the way up to pi halves of r squared d theta. That would work. If you integrate from negative pi halves all the way up to pi halves, you get half of it, and then, of course, you double it. So you have that option as well. And you'll see as we go through, you can set these up in any number of ways. And symmetry is always a good thing to consider. So I'm not going to go ahead and rework that one with the different intervals of integration. But I will verify that we get 6 pi. Now, here are 2 different ways to do this. If you happen to have your calculator in polar mode, and you probably, if this were a calculator question, you would probably be in polar mode. You would probably type in 2 plus 2 sine of theta to see what the graph looked like. So let's wait for my calculator to load. And if you have a calculator, go ahead and get ahead of me. Remember, you still have to be in radian mode all the time. But POL is for polar. Come on, Smart View. Spinning beach ball. Makes me long for the summer. All right, here we go. So mode, I'm going to polar mode. I'm in radians, so y equals, I'll clear that out, 2 plus 2 sine of theta. All right, so we don't need to graph it. We just go to the home screen now, and we type in our integral, which is 1/2, so 0.5, math 9. We're going from 0 to 2 pi, and we're squaring the radius. So where is our equation for r? Alpha trace. There you go. So just like with function mode and parametric mode, you can recall what's in your graphing screen, and then we can square that. And, of course, d theta when you hit the t variable. And that should give us 6 pi. And if you want to verify multiply 6 pi, you get that. So we did it. Yes, Tyler? It does matter. Yeah, in general it does matter. But notice these parentheses that they open for me, that sets off the entire integrand. So the nice thing about having your equation in y1 or r1 or x sub 1 is you could just square that and not have to worry about parentheses. But when in doubt, it's better to have them than to leave them out. So if you want to put more parentheses around the r, like this, if you wanted to put an extra set because you're not sure, it's better to have them and not need them than to need them and not have them. That didn't quite work, did it? I need to insert another one. Yeah, that worked. Okay. That's going to give you the same answer. All right. Okay. Oh, yeah, the other way I want to show you. You don't have to be in polar mode. If you get out of here and we go back to just rectangular mode, you might not actually sketch the function in polar mode. You might not even care to see what it looks like because you know what it looks like. So in rectangular mode, 0.5, math 9, you're integrating it still from 0 to 2 pi. Yeah, I'll do pi times 2. The only thing is we can't recall it from R1. That's the only bad thing. So we'll have to type it in. So Tyler, here's the parentheses where we would need it. Parentheses, 2 plus 2 sine of our input, close it for the angle, close it for the quantity, and then square it with respect to x. That'll give you the same answer. Okay? Does that answer your question?
I was asking if like
No, go for it. What?
I'm not sure how to explain it. Like, can you put the squares like outside the big parentheses?
Way out there? I don't know. I've never done that. Let's see. I see what you're asking. I don't see why. No, because as soon as you click to the right, it goes to dx. So those are the default parentheses that it always has around its integrand. So you need to introduce your own parentheses. Okay, cool. Any other comments or questions or things to remark about this first example, example number 1? Oh, because remember, once we get to our integral setup, this variable and this variable, they could be anything. It could be u du, x dx, m dm, p dp. The important thing is we got to the integral setup. If I keep it in polar mode, then the only advantage is I can refer to 2 plus 2 sine of theta as r sub 1. Okay? That's why the integral setup is so important. Because the integral can represent an area, it can represent a volume, it can represent an arc length. And once you get it set up, then choose any variable you want. If you don't like theta, change it to u, change it to x. Okay? All right, example 2. Find the area of one petal of r equals 2 sine of 3 theta. So what can you tell me about this rose curve? Bless you. Length of 2. Only 3 petals? Yeah, because it's an odd number. It's going to trace out once from 0 to pi. Remember, if we only see n petals, it traces out from 0 to pi. Bless you. To see twice as many petals, we have to go twice as far to 2 pi. And it's going to have what type of symmetry? Y-axis or x-axis? Y-axis. Okay. So knowing how these things are tracing out is important. And I'm going to start all of them as if it were a non-calculator question. Plug in a 0 first. Okay. We're pointing due east at 0 radians. What do you get when you plug in a 0? You get 0. So we start at the pole. Now, if I want to figure out the area of one petal, this thing might do something like this and come back. So notice that if I know what one of these polar zeros is, then the very next polar zero is going to be an interval that encapsulates or defines one petal. Yes? So yes, very good. Instead of trying to figure it out, because the 3 theta is going to make it hard, all we need to do is integrate between any 2 consecutive polar zeros. So in this case, let's go ahead and just set it equal to 0, like Colin mentioned. All right, so if I divide through by 2, I get sine of 3 theta equals 0. Now, if you remember how to solve equations with multiple angles, you just say, okay, sine of what angle gives you 0? Where is sine equal to 0 on the unit circle? At 0 and pi. You want to get the first 2, okay, within the first revolution. Okay, so 0 is one of them, and pi is the other one. Now, those are not equal to theta. Those are both equal to 3 theta. It's like taking the inverse sine of both sides. And I found the first two, 0 and pi. Now if I solve for theta, I get 0 divided by 3, which is 0, and we knew that one. But the next one is going to be at pi thirds. Yeah. So as we rotate from 0 to pi thirds, it's going to do something like that. And of course, the length is 2. So really, if we want to find the area of one petal, we can set it up now. The area is going to equal, what goes in front for all area formulas? 1/2. The integral from 0 to pi thirds of r squared d theta. And r is 2 sine of 3 theta. Now again, if you wanted to do this by hand, it's not showing up. Come on, come on. If you want to do this by hand, you're going to have to use the power reducing identity. There it is. If I shake it like an Etch-a-Sketch, it works. Come on. Come on, boy. Come over here. All right, there it is. All right, so we're not going to do it by hand. Once we get it set up on our calculator, on our paper, we're going to go to the calculator. Have I graphed it in polar mode yet? No. So I don't care what mode I'm in. Currently I'm in function mode, right? Let's say I was in parametric mode. I just did a parametric problem. Now I came to this problem, and I'll just type it in. It's 0.5, math 9, and then it's going to be from 0 to pi thirds. 0 to pi divided by 3. And here's the important part now. Since I'm not referring to R1, I got to type it in. So I need another set of parentheses, not a 2, but parentheses. There we go. 2 sine of 3 theta, close it for the angle, close it for the function, square it, and then with respect to t. So from the home screen, it doesn't matter if the variable is x, t, or theta. All right? Because when you say dt, it's going to treat whatever this is as a variable. So that should do it, right? Double check, triple check. How does it look? Looks good. Okay, so there it is. It's 1.047. All right, so the only reason you would need to be in polar mode is to see the graph. That's really the only reason you'd be in polar mode, to see the graph. And then if you happen to continue then to integrate it in polar mode from the home screen, that's when you can just refer back to R1. Okay? Yes?
So if it were saying that it wanted you to find the area of the entire...
Hey, that was my next question. Yeah. What if it said define the area of the entire rose curve? Very good. You would just find the area of one petal and multiply it by 3. Very good. What if that had been 2 sine of 4 theta? Then you multiply by 8. Okay, good. Because remember, if it's an even coefficient of theta, you see twice as many. Okay, very good. Very good. So integrating between consecutive polar zeros, any consecutive polar zeros, is going to be enough to find the area of one petal. All right, so good so far, so far, so good? Okay. Letter 3. Find the area of one petal of r equals 4 cosine 2 theta. All right, you set it up on your iPad flash paper, and I'll set it up here on my iPad flash paper, and we'll see if we get the exact same thing. Okay? every day.
So is it okay if you, instead of setting it to like 5/4 and then you get 3/5, you can just do it like, if you feel like the counterclockwise, because I got the same intention that time.
Oh, yeah. You just, instead of rotating around,
All the way.
yeah, you went the other way, negative pi halves. Yeah. Any two, as long as they're consecutive polar zeros. If they're non-consecutive polar zeros, that doesn't work. Yeah. So I found my zeros. I set it equal to 0. And I said that cosine was equal to 0 at pi halves and 3 pi halves. Hampton went negative pi halves to pi halves, which is fine. He backed up a half cycle and then went to a full cycle. So that's fine, as long as it's between consecutive polar zeros. But those were equal to 2 theta, because that's what our angle is. So then when you solve for theta, you get pi fourths and 3 pi fourths. Yeah.
So if the number of pedals doesn't matter if you're just trying to find the area of one.
Correct. Yeah. If it says 1 pedal, you just find consecutive zeros and you integrate from there to there. So here's the setup that I came up with. 1/2 from pi fourths to 3 pi fourths of 4 cosine of 2 theta squared. Hampton probably had a little different one, but he did get 6.283. So again, if you're going to do this by hand, you're going to have to use the power reducing identity. But if you're doing it on the calculator, and I did this one back in polar mode. I was in polar mode. If I'm allowed to use my calculator, I'll probably honestly go to polar mode, and I'll hit zoom 5, and I'll see the pretty rose curve. And now I'll go to the home screen, and the advantage then is I can refer to my function R by hitting alpha trace number 1 instead of having to type it in. But that's not that big of a deal, having to type it in. These functions aren't, incredibly long. But don't forget the 1/2, right? It's so easy to forget the 1/2. Just like when you're doing the disc and washer method, you might forget the pi or the 2 pi. The magic number out front, okay? Is that equal to 2 pi? Yeah, it looks like 2 pi to me. Good. If you type in math 9 and then you forget to put the 1/2 in the front, just divide the whole thing by 2. That's fine. You can do it that way. Just don't forget the magic coefficients in front of all of your integrals. All right, so good so far? You want to verify this one using the power reducing identity? No? Okay. But if you were, you would simplify this to 4 squared is 16. Don't miss that. And then 16 times 1/2, you would have an 8 there. And then you would use the power reducing identity, which would make that another 1/2 times 1 plus cosine of what would be the new angle? 4 theta, right? You half the power and you double the angle. And then this 1/2 can come out front, and you end up with 4, the integral from pi fourths to 3 pi fourths of the quantity 1 plus cosine of 4 theta. And that is a pretty nice looking integrand. So if you do that, you should get 2 pi. All right, sweet. And again, if they ask you to find the area of the entire rose curve, since we found 1 pedal between consecutive zeros, you would multiply this one by 4. Okay, sweet. Example 4, speaking of, find the area inside one loop. Inside one loop. Just outside loop 410, 1604, right? What does this one look like? If I just gave you R equals 4 cosine of 2 theta, you would say that's a rose curve, right? With how many petals? 4 petals. But it's equal to R squared, not R. So if I wanted to graph it on my calculator Medora, I'd have to go R is equal to plus or minus the square root of 4 cosine of 2 theta. Now, it doesn't really matter if it's plus or minus, because we know in polar mode, as we saw with the circle yesterday, if the radius is -4 versus +4, it's just going to trace out from a different starting point. But notice, bless you, by taking the square root of that, my petal length is no longer 4, it's 2. Is this always going to be positive underneath the radical? No. If you think of what the graph of 2 theta looks like, first of all, the amplitude is 4, so it goes up to 4 and goes down to -4, and cosine looks like that. And because we're seeing 2 cycles from 0 to 2 pi, this would be pi. So we actually have some negative numbers, don't we? What's going to happen to the graph then when we try to take the square root of negative numbers? Yeah, it's not going to graph anything. Is it a vertical asymptote, though? I don't know. This one's curious. Let us see. I'll type in the square root of 4 cosine of 2 theta, and I'll hit zoom 5. It looks like infinity. Let's slow it down a little bit. Let's do a smaller t-step. Right? It's starting like a rose curve, and then it's supposed to be coming down here, but it's not. And then it comes back up here, continues this loop, and watch. When it hits the pole, it's supposed to continue up here on the positive y-axis. And then it completes this. So did you see my cursor tracing out the parts that weren't there? The parts that I was tracing with my cursor were the 2 imaginary petals from this supposedly 4-petal rose curve. Okay? So if 2 of the curved petals are imaginary, they're not really there. We do end up with a 2-petal rose curve that is actually given a different name. It's called a lemniscate, and it is the infinity symbol. The infinity symbol is nothing more than a 4-petal rose curve with the 2 vertical petals being imaginary. Okay? And because it's such a special symbol, it has its own name, lemniscate. Now it's pretty easy to remember, because figure skaters, when they do their preliminaries, they don't really show that on TV very much anymore. One of the things they have to do is figure 8, right? Figure 8 lemniscate. They have to actually sit here and skate in a figure 8 backwards and then flip around at the juncture and go forward. It's kind of interesting to watch, kind of like curling.
That was like the French word we learned, lemon.
Oh, there's like definitely a lemon theme going on, right? And hey, look, my Clorox disinfectant wipes have lemon scent in them. Lemon scent. Yeah. So yeah, lemniscate, limison was the other one. I guess that's close enough, Tyler. Lemniscate, figure 8, lemniscate. Okay, so how am I going to figure out, first of all, the area of one loop? Did you see how it started tracing out? Let's go back to the window and change the theta step to 0.005. I think that was good. Notice, okay, to see what it did? It started over here at 2, which is the square root of 4, the petal length, and the first polar 0 gave us half of one petal. So could we find the area of just half of one petal and then double it? Yeah, all of these petals are going to be symmetric through the line that goes, the length line, okay? So you can actually do this. You could set it equal to 0, and you can solve. Square both sides. You get 4 cosine of 2 theta equals 0, so cosine of 2 theta equals 0. Cosine is equal to 0 at pi halves, but that's equal to 2 theta, so theta is equal to pi fourths. So I don't need to find 2 polar zeros in this case, because what I could do is I could find the area. It's equal to, leave a space, it's 1/2 the integral now from 0 to pi fourths of, and here's where you got to be careful, r squared, they already gave you r squared. You don't have to square it again. So it's just 4 cosine of 2 theta d theta. But that's only going to give me half that petal from here to here. All I do now is what? Double it by putting a 2 in front. And that makes it a little bit nicer. Let's go ahead and integrate this one by hand, because we're not squaring it. So that just becomes a 1 in the front. So the 4 goes along for the ride. The antiderivative of cosine of 2 theta. Well, I generate an unwanted 2, so I'm going to have a correction of a half. The antiderivative of cosine is positive sine of 2 theta. And then I evaluate it from 0 to pi fourths. So now the front becomes a 2. And when I plug in, I get sine of twice pi fourths, which is pi halves, minus sine of twice 0. My wife doesn't smoke, and I smoke twice as much as she does, which means I still don't smoke. Twice 0 is still 0. That's the point I'm trying to make. And don't do drugs, everybody. Smoking is a drug, nicotine. Sine of 0 is 0, so we get 2. So the area is 2, it looks like. The area of the infinity symbol is 2 in this case, when the petal length is 2. Let's verify. I wonder if we can verify. Let's go to the home screen. I'm going to go, 2 times a half, so I'll just go math 9. from 0 to pi fourths. And this should be an okay interval to integrate over because I'm not integrating through imaginary numbers. If I were to integrate past pi fourths, I'd be in negative under a radical land. So I do have r in y1, so I do want to square it. So alpha trace, bless you, 1 squared d theta. Why was there no 1/2 in the front? I doubled it, right. So I went from 0 to pi fourths, which was half the pedal, doubled it, got rid of the 1/2, and there it is. It's 2. Okay. So good so far? Having fun? Polar area? Kind of nifty. I like it. Do you like it? It's all right. Okay. Let's see if we have time this one before the stand comes. We're in here. Let me, let's see, till 11:20. Yeah, we're not going to have time. We'll stop right there. That's enough to digest for today. Polar area, 1/2 r squared d theta from alpha to beta.